Good morning. Thank you very much for coming to our workshop. So as I already told you, I heard half of it because I was watching outside for more guests. My concern was privacy protection in biometric data. And I'm going to talk about one of the central projects in our research, which focuses on generating keys from facial data, from facial images, while preserving privacy as much as possible. And this work has been done in collaboration with Cor Dunkelman and our student Mahmoud Sharif. So we have users in our system, and we want to generate keys for them. And the most common way to do that is to use passwords. Passwords have been used for many years, quite successfully, but we do know several problems about using passwords. So first of all, people tend to forget passwords. The more random the password looks, harder to remember it. And if we forget it, there are this kind of recovery mechanisms that have their problems. So the other problem is that if you type your password, someone can just watch what you type, see what you're typing from behind you. And so, that's a problem. Your password is revealed. Another problem is that most of the passwords have really low entropy. And studies show that the most popular password is 1234. You can go to 8 if you're required to type 8 lengths of 8 password. Well, it's hard. It's exactly the same problem because it's hard to remember random passwords. So passwords that we type actually have no entropy. Another problem is that if we already have a good password, it's hard to remember it. We will reuse it in different systems, and we tend to do that. So this is another problem in the password that we want to address. So there have been a suggestion to use the biometric data instead of passwords. So the information that user provides is instead of the password, we just take it, his or her biometrics. And there are several problems with this approach. So the first one that you probably tell me, well, how can you differentiate between a picture or a real person? And this is true for some of the systems that were deployed. They got confused. You can just log in with a picture of someone. This problem we do not address in this talk. We talk about mostly privacy and not security. However, there are solutions that can be applied to solve this problem. For example, you can use 3D information, you can use movements, you can ask for a person to say something, and you can differentiate between image and a real person, and actually vision problem that is solvable. So I will not talk about this one. However, there are other problems that I will address in this talk. If an adversary gets hold of the key of, it can actually reconstruct your biometric, because most of the systems just store this biometric in the clear. And as already told you, if your face is stolen, what can you do? And to solve this problem, there's this line of work called cancel biometrics, where you use biometric of a person with some other random information. You incorporate them both, and then you provide the key. If something happens to the key, if it's compromised, you can just change the random string, and then you don't have to change the biometrics. However, the privacy of the users is not so easy to achieve. So you give your information to the system, it's in the server, and God knows what's who is going to misuse it in which way. So what we want to do, we still want to use images for key derivation. And one straightforward solution is just to take an image and apply exactly the same technology as we do with the password. We take a password, we hash it, and we generate a key from this. So instead of password, just take pixels or some biometric features and do exactly the same process. Then you don't have to store the actual image in your system. After you hash it, you just don't need it. And you can go back from the hash. However, we can't in practice use this idea because biometric data is fuzzy. What do I mean by fuzzy? If you take, for example, two images, one after another, exactly the same room, with exactly with the same camera and lighting conditions, like a second apart, you actually see that these two images are taken in these conditions. They look really, really similar. And recognition systems will recognize these two images as the same person. However, if you look at the values of the pixels, so more than 81,000 of the pixels have different values in these two images, corresponding pixels, I mean. And only about 3,000 are the same. So these technologies that we use with passwords will not work. However, we still want to do that. So how can we do that? The idea is that we want to reduce this information this difference to 0. So first thing that we can do, we can use feature extraction. This is vision technology. People worked very hard to creating features that can take images taken in different viewing conditions, remove these variations, and make them closer. You can do recognition well. You can identify a person. However, still, you will not have exactly the same values. Besides, all these features are usually real numbers. You have a vector of real numbers. So we should do something more to use cryptographic constructions. And there is another line of work in cryptographic community that developed noise-resistant hash functions where they use error correction and helper data. So these two things we're going to do, and we're going to add something in between. So we're not the first to address this problem. There have been some work in this area just to do all privacy preserver, some kind of biometric systems that use or images of faces or some other biometric information and provides key from them. So to reduce this noise that I was talking about, there are a 3-step noise reduction process. So the first one, we do feature extraction. We go from pixels to biometric features. We aggregate it in some way and remove all this difference that comes from difference in viewing conditions and some distortions in the face. Then we end up with a vector which has some lengths, and those are real numbers. And they're not exactly the same if we take two images of the same person. So we go through a binarization process, and this binarization process, it converts real numbers to binary strings in a consistent way. What do I mean in consistent ways? That at the end of the binarization process, we wish to have as many bits broken as possible. So we want two images to get exactly the same binary strings. Unfortunately, we can't do that. We still have some errors that we correct using error correction. OK, so now I will go through all these steps, and I will point out what problem with privacy we can get in when we do these things. And actually, we saw it in previous work that people do get to these troubles. So about feature extraction, that's what vision does. There are two groups of methods that extract features. One method, so it's actually my names. It's not they called this way. I call them. One is user-specific features, and the other is generic features. What is user-specific features? They require a training stage on people that you want to recognize. And they're quite discriminative because you train for these people. So the process that is done here, you actually assume that all faces in your training set can be approximated by a linear subspace, and you just learn this linear subspace in some way from people that you train on. The other group of methods are generic features where you don't need training stage. You extract some low-level features, you aggregate them in some histogram, or you do image transfer like Gabor features, and then you use it in your classifiers. So these generic features do not need training. So what is the problem with the user-specific features? Because we train on users in the system, and they're required to store this information, their models, on the disk in clear. And as you can see here on the right, we have an image of an actual user. It looks a bit funny because we normalize it to 0 mean and unit brightness. And on the left is one of the basis images that were learned from people. And you see that it really looks like the same person. Not all people will appear there, but you can reconstruct back easily. So there was a previous work that they spent a lot of effort to make everything private, and they have this analysis of security and privacy, and everything looks fine. But the first thing that they did, they used feature faces to extract features. So that's it. From this point on, you don't need your system. You can just hack that. So we don't want to use this kind of features in privacy-preserving system. So what can we use? We can use generic features, but we also should be careful here because many generic features have correlations between their channels. And if they don't have correlations, they have high-order dependencies. Like in Gabor features, you don't have correlations, but you have high-order dependencies. And when you convert it to a key, these dependencies will flow into there too, and you actually have key of length k, but your entropy is much lower. So we will look at this problem closely later on. OK, next step is binarization. It's essential for cryptographic constructions because they need binary strings, not real vectors, and they only can correct a limited number of errors. Some previous work claimed that after you do binarization, you can go back mathematically. That is why it masks information. We're fine. This is true mathematically, but it's not true in practice because you can approximate. You have the statistics of faces, and you will not get exactly the same thing, but you will get really, really close approximation. So this is not true. But we still need this binarization process for cryptographic constructions. We can do it by sign of projection, and that's what we do. I will explain about this later. And you can do quantization. What is quantization? You have this channel of information, and you want to quantize it to get a bit. So the most simpler thing, think about the mean of some feature for the entire population, and you have the readings of specific person, and if it's above the mean, it's 1. If it's below the mean, it's 0. This is the simplest thing you can do, but it's not very discriminative. To get it more discriminative, you have to divide it to smaller intervals, and then you have to store information about these intervals. And unfortunately, this information actually reveals additional private information, so we don't want to do that either. So we'll go with the projection. OK, so now we have these binary strings with some number of bits which are broken, and we want to generate keys from this representation. So we use fuzzy commitment by Jules and Wattenberg. There are other constructions that address the same problem, like fuzzy vault or fuzzy extractor. Fuzzy commitment is actually a private case of fuzzy extractor, because in fuzzy commitment, we assume that binary representation is uniformly distributed. It's not always true. If it's not true, then you can use fuzzy extractors to extract a uniform string from that. You certainly pay some entropy for this. We do it differently. We provide uniform distribution with other means, so we don't need fuzzy extractors. We just go with fuzzy commitment. So what do we do here? We present. So we said that we generate a key from images. This is not true. What we do, we just generate a key randomly. We encode it with error correction codes, and we XOR it with a binary representation. And from this, we get S, which is called a helper data. And we have to store this helper data or with the user or somewhere else. This is actually a problematic point, but we will not talk about this now. So we have this S string. Then when we want to generate a key, we have this representation. The user comes second time. He presents its biometric. It's similar to the first one. It's not the same. And we XOR it, we XOR it with S. And then we get a string which is similar to that one after encoding, but it's not exactly the same. We decode it, we correct errors, we get the key. So you can hash the key if you want for various applications, but you get the idea how it is done. If you have a different string or you have a different S, you will not get the key. Okay, so about previous work. If everything is done correctly, they end up with short keys. If the key looks long, there is kind of cheating there. Not cheating, problems. So the first problem is that we saw that people use strings which are not uniformly distributed because of the correlations and other things. And they apply the fuzzy commitment scheme. So you can't actually trust the length of the keys that get from there. The other thing that happens is dependency between bits of the biometric samples. Again, you get a long key, but you can guess it more easily. As I said, auxiliary information can leak, auxiliary data can leak personal information, such as feature extraction process or binarization process with quantization and other things. And the most hard one to achieve, if an adversary gets hold of a cryptographic key, we should not be able to construct the biometric data. And it's not true in previous work. Most of the previous work, if you get the key, you can go back to the biometric. OK, so from here, we have the security requirements and privacy requirements that we define for ourselves. So the first one is consistency, which means that we want the system to recognize the true users, the genuine users as themselves. And in the biometric language, it's called low false rejection rate. So we shouldn't reject the people that are in the system. The other one is discrimination. We do not want imposters to enter the system, to impersonate an enrolled user. And in language of biometric researchers, it's called low false acceptance rate. And then we have the weak biometric privacy, which means that given the helper data, the S string that I showed you in the previous slide, we cannot, it's computationally infeasible to reconstruct the biometrics. The strong biometric privacy says that you get also helper data and in addition the key itself. And having both helper data and the key, you cannot reconstruct biometric. And the last one is key randomness. It talks about security. If you get the helper data, the key looks indistinguishable from random. So these things that we want to achieve in our system. OK, so now I've finished with the requirements. And with previous work, I will tell how we have this half-done system. It's proof of concept, and we're trying to improve it. So I will talk about this system. So before feature extraction even done, we have to align faces. Because people, when they come, they move their faces, and recognition algorithm, identification algorithms, needs these two images to be aligned. So in regular, non-secure, in a system that doesn't care about privacy, we just store the image of each user as a model in the system. And when you have a new image, you just put the eyes and the nose and the mouth of the same person in the same positions. We do not save the image of a person in our system. So we can align it. And without alignment, the recognition will not work. So we have to do something. So we align it to a certain canonic positions. So my face is very different from Or's. But we will put my eyes and his eyes, my nose and his nose, and my mouth and his mouth, exactly the same position. What will happen to be? I will have a larger face, right? So, and it will distort my face. It will be easier it will be harder to recognize. We will look similar. Okay, so that's why I'm talking about this. I'm trying to tell you that if we want to have privacy in our system, we will pay a price, and this will be price in recognition, in identification abilities. So it's a harder problem in terms of vision. Okay, so we find these landmark points with some automatic detector, and we compute 5 points from there, like corners of eyes, corners of mouth, and the tip of the nose. We take 2 images, one frontal, one profile. Why we need 2? Because we want more information, want more entropy. We can't take any other image except from these 2 because they will be correlated with the other ones. Because in these 2, we actually see different information. each other image between the profile and frontal you will see similar information. This will lead to correlation. So after we've done that, we extract local areas in 21 regions from the face, and we construct features. We just use popular features from vision, like SIFT and histograms of oriented gradients, also color. OK, so now we have this vector of real numbers in R and 1. And we want to convert it to a binary string of size n2. So how can we do that? We do this binarization by projection. So here you have these functions that we do. We project a vector x, which is a biometry, on a number of hyperplanes. We take their sign and we shift it and scale it to be 0 or 1. Let's look at the geometry of this. We have a hyperplane wi, and we have an image of the person. And let's say if we project it, it falls on the positive side. So the bit, according to this function, that we will get is 1. If this image falls on the negative side, then according to this function, we'll get 0. OK, now we have a second image of this person, and we want it to have exactly the same bit, right? So we want it to fall on the same side as the first one. So if we want it to be 0, it should fall on the negative side. If we want it to be 1, it should fall on the positive side. So this is the idea. This is good for one person. But if you have many people, so what we should do, so still we want images of the same person to be on the same side of the hyperplane, but we want images of different people to have different bits. So we want it to be on different sides of the hyperplane. But it's impossible to do with one hyperplane if you have more than 2 people. So what can we do? We add more hyperplanes. So some of the people will have similar bits, the same bit. Some of them will have different bits. But in the entire representation, we will have differences between people. OK, so in our binarization algorithm, we want consistency discriminations. That's what I get if I follow these ideas that I just presented. We also want no correlation between bits. And I will just do it the following way. I will construct my hyperplanes so that they will be orthogonal as possible, And then when I project my representation of these orthogonal hyperplanes, I hope to have no correlation. I will explain you in a moment why I'm optimistic about that. And I also want high entropy. How can I achieve high entropy? I can just pass all my hyperplanes in the middle of the space. So approximately half of all people will be on the one side and the other half on the other side. And I can do that. So we used an algorithm in Vision that has approximately the same requirements, not exactly. We adjust it to our problem, and it works OK. Now, how can I get rid of dependencies between bits? Faces, fortunately for us, faces in the same position and with same illumination, they're approximately Gaussian. They're not white Gaussian. They're Gaussian like, what have I done? OK. They're Gaussian like that. So if I whiten it, and then I project it on orthogonal basis, I will get independent bits. This is theory. So if I'm sure that I have a Gaussian representation and it's white, then I'm sure that I will have independent bits if the projections are orthogonal. OK, so we do exactly this, and we hope that, and I'll show you that we actually get bits close to independent. The full system looks like that. We have 2 images. We take 2 images of a person. We extract features. We binarize them. We remove dependencies. Then we get a key randomly. We encode it, and we XOR it with binarization. We get the S, the helper data. Then for key generation, we are presented with a new biometrics, the same S as before. From the biometrics, we extract features, binarize it, then we XOR it with S, and we decode and hash, and we get the key. OK. So if you listen to me carefully and you understand a little bit in learning and vision, you will ask me, wait a second, but you said that we shouldn't save we should save no information about the users that are extracted during training with our system. And I learned my W matrix, the one that I projected with this orthogonal hyperplanes from users. I showed you images of people a few slides ago. That's true, but what we do not learn this W on people that we want to recognize. We have a set of people, online set, that we use to learn W, and then we use it for every one of the systems. And since we didn't train W on these people from the system, they don't include any information about these people. So you can ask, how can it be done? You do recognition. How you can learn something that's so generic? This happens because we do not learn if this person is Alice and this person is Bob. What we do is a concept given two images if they're the same or if they're different. And this you can learn on some population and apply it on another population because faces are faces. They have same properties. OK, so that's how we achieve W, which do not reveal any private information. So a bit about the results. We need to learn this W. So we found a number of data sets with images of people in frontal and profile. We extracted about 1,000 people for each one of the views. We took a number of images, as much as we could get from there. And we learned this matrix W with 800 hyperplanes for each one of the faces independently. We learned for frontal, and then we learned for profile. And then we ran evaluation tests. So first of all, we wanted to check how the recognition is doing after all these things that we needed to do to protect privacy. So we don't do error correction. We don't do fuzzy commitment yet. We just do binarizations, and we compare. So we took 2 frontal images, 2 profile images of 100 different people that were not used in training of W. And then we ran the standard benchmark that is done in vision with cross-validation. I will not go into details of that. And we got the Roc curves. I will show it in a minute. So what is this? Actually, I will show it now. What is the Roc curve? So we have a representation of the person. We have a different representation of the person. And we measure the distance, the Hamming distance, actually, because they're already binarized. And we can set different thresholds for Hamming distance. And for each threshold, we measure how many people, how many false positives we have. What is false positive? People, imposters, are recognized as users. And for each false positive, we also compute true positive, how many people are recognized as themselves. So actually, we had this Roc curves, and I will go to this key generation a little bit later. OK, so as you see, the best Roc curve could be if in 0 false positive, you get 100% recognition. It means that we do perfectly. You can't do better than that. Well, it's a bit optimistic because it's only 100 people, but it's a good start. If we compare it to random projections, what is random projections? Instead of learning this W from people outside the system, we just randomly select orthogonal bases. It works a little bit worse than that, and we will see more differences in key generation. So to generate keys, we took 100 people, this from the previous set, genuine users, and how we get the imposters, we just take all the difference, all the pairs that are not the same. So it's 9,900 pairs that we can create from 100 people. OK, so key generation. So there is a trade-off between how many errors we can correct and the length of the key. And it's quite intuitive because we have a given given number of bits. Some of them go to correct errors, and what remains goes for the key. So the more errors we need to correct, the shorter the key we will get. And the problem is that after all this hard work and vision, we still have many errors to correct, unfortunately. So we want to get some numbers to show you to get to see how long we can get in theory with the key length. And this is spherical bounds. It shows the connection between the length of the code. In our case, we have 1600. It's 800 from frontal, 800 from profile. T is the maximum number of errors we need to correct. And K is the length of encoded messages, what we want to get at the end. And we want to get K as far as possible, as high as possible. And this is the theoretical bound that we used. And you can see the results that we get. So unfortunately, we have to correct about 600 errors, more or less. And what we get if we want a key in a bound, I mean, 80 bits, we will have 30% of false rejection rate. This is quite sad, because 30 times when we enter the system will reject us. But if we go a little bit lower in K, we go to 70. Then things get better. We only 16 times of attempts to enter the system of genuine user will get rejected. And the numbers are worse for random projections. OK, so this is a theoretical bound, and now we want to do error correction. And it wasn't easy. We thought about it, and then we realized that binary codes can't work. They can't correct as much errors as we need. So we said, let's go to Reed-Solomon or some non-binary codes. So for example, if we use Reed-Solomon and we take in the representation, we take every 5 bits and we create a word from it, and then we go from 50 to 31. We will correct some errors, but the problem here is that, that the probability of error in a bit, as I told you, is 30%. So 30% of bits are incorrect, and we need to correct them. If we go from bits to symbols this way, we just take blocks of 5 bits, the probability of a symbol, error in the symbol is very high, 0.8. And so we've done nothing by doing this. So what can we do? We will do repetition. So we did the following thing. You take the representation, the binary representation, and you place it 5 times, one under another, and you form a matrix like that. And now you take these bits not as a row, but as a column. And what happens now, all bits in the symbol are identical, are the same. And now if we do Reed-Solomon with the same numbers, we will get the probability of error in symbol is the same as the probability of error in a bit. So we can correct errors now. What we do the following. We have this X. We repeat it 5 times as rows. And what we have here in encoding, we take a key, we encode it, and we reshape it as 31 by 5. So we put this 31 5 times, like row or columns. Sorry, not why it goes. And we repeat it Q times. What is Q? It's as if the representation is of some length, and we have 31, so it's the length of representation divided by 31. This is the Q that we can fit inside the X. So when we XOR it, we get the helper data. Now we have actually 5 rows of helper data. Then we decode it. We get the new readings of X, which is a bit different from the first one. We XOR it with the helper data, and then we decode it. Now look what happens. We have the same bit here. This was the same bit in a coded key, but it were different bits in X. So sometimes we had a problem, sometimes we don't. Sometimes we have an error in a bit in X, but sometimes we don't. So now we have Q such bits, and we can do majority vote over this bit. And if we do the majority vote, we hopefully get the correct one. So after we do this decoding, after we do this XORing and majority vote, we get the string C, and then decode it and get K. Okay, so now we can correct errors, but we have a security problem in it. Why we have a security problem in it? Because consider that we are guessing 15 bits of X. If we guessed 15 bits, first 15 bits of X, actually we know it's in every row. We know the entire column. And if we know the entire column, we just have the ECC of key. So actually, even though we start with 75-bit key, we get only 15 bits of security. Well, this is not good news. What can we do? We can do a secret sharing solution for that. So we generate our key by XORing some number of subkeys. And we do exactly the same procedure for each one of the keys. We just add it. We just add in this matrix. This was the first one. Now we add the second one, the third one, till R. So how many keys we can get, it depends on the length of the representation we have here. And now we have to guess. We still have these 15 bits that will reveal the first subkey. But we need the second subkey and the third subkey. So after all, we have 15 R bit security. So increase it R times. We ran experiments with it, and the length of our representation allowed us to use R equal to 3. And these are the results. The key length, as I said, is 75 bits. The security is 15 times R, so it's 45 bits. False rejection rate is decreased by half. It was 16% with 60 bits. Now we have 75 bits length with only 8% of rejection. False acceptance rates is not 0 as before, but it's really small. Encoding and decoding times is very fast. So it looks like we got higher number than in bound, theoretical bound. Seems weird, right? So actually we're cheating here because there in the bound we use the length of n was the length of x. Now we use 5x's. It's longer. So that's why we get better numbers. But these are real numbers. This from the experiments on real people, and that's what we have at this point. 75 bits, 45 bit security with really good false rejection rate and quite acceptable false acceptance rates. How much time do I have? I didn't look. Hours here. Okay, so security analysis. So remember this slide that I showed you what we want from our system, and I said that we want consistency, we want discrimination, and we got it. It's quite good. Now I will talk about the privacy issues and security issues. So the weak biometric privacy falls from the strong biometric privacy. What is weak biometric privacy? We have the helper data, and we can't reconstruct the biometric. In strong biometric privacy, we have the key and the helper data. We can't reconstruct the biometrics. So if we hash the key at the end of the process, then given the helper data and the hash of the key, we can go back to the biometric, and this is accomplished by using uniformly distributed strings in Jules and Waterberg construction in fuzzy commitment. So now we should show that we indeed provide uniformly distributed strings. Otherwise, we can't trust this. How are we going to show it? We say that we have no correlation between, if we show that we have no correlation between bits and high mean entropy, then we can say that we have uniform distribution. So there are two ways to show that we have no correlation between bits. One is a statistical measure called degrees of freedom that have been used heavily in previous work. It should we should get the number which is equal to the length of the representation. We have 1600. This is the length of our binary representation. And we get 1050.71, which is not that bad. It's quite good. So where it's come from? If we have uniform distributions, then we should have really, really small variance. And we have really small variance, we will get these numbers. I don't have time for details, unfortunately. Another way to do that is to actually, we started to work with Gaussian data, and then we did everything right. We removed correlations, and we projected on orthogonal hyperplanes, which means that we don't have correlation. It also means independency, statistical independency for Gaussian data. So we looked at the covariance matrix, and we see it's diagonal. So it's the other way to see that there is no correlations. And if there is no correlation, we can just sum the mean entropy of bits in our representation. And the mean entropy of bits is quite high. The deviation from 0.5 is small, what you can see on the bottom line. And after we sum it, we get a number which is close to the previous one and also close to 1600. So we're quite optimistic about the uniform distribution of our strings. Now, the last one that we want to show is the requirement on security that given a key, given a helper data, the key should look random. So we should show that the entropy of K given S, K is the key, S is the helper data, is high. So what is K? K, we run the decoding on X XOR S. If X is uniform, and that's what we showed a minute ago, all possible results of this decoding have almost equal probability regarding of S value. So we can just remove S from here, and that's what we do. So we have a high entropy. We show that we have high entropy. OK, so this concludes all the requirements that we wanted. And that's it. What have we showed? We showed a key derivation method that achieves good consistency, discriminability, high entropy representation. We showed that it satisfies all the requirements that we wanted about security and about privacy. And in addition to that, our algorithm for identification is very, very fast. We just take an image, extract features, project it on a matrix, which is really fast thing to do, and we get the result. What is good for? So you get a key. You can do whatever you want with that. You can log in with this system. You can use it in databases, actually, or we'll give an entire talk about how to do that later on. What we're going to do next, we want to improve. We want the keys to be longer. We have 45-bit security. We certainly want it to be higher. So to do that, we need to improve vision, to make less errors in our strings, to correct. We should improve the error correction codes. And that's it. That's what we want to do. Thank you very much.